Hello everyone, welcome to my video. In this video, let's talk about impact. 2 videos ago, we explored the conservation of linear momentum and the principle of impulse momentum. So far, we have many tools in our hand, including Newton's second law, work energy, and impulse momentum. With all these in hand, we are ready to talk about impact. As the name suggests, by definition, impact is defined as collision between two objects that creates a relatively large contact force between two objects over a short period of time. There are 2 types of impact we care about: direct central impact and oblique central impact. We'll start with the direct central impact, and this is when objects are moving with aligned centers. For example, here we have 2 tennis balls, M1 and M2, and they are centrally aligned, or we say they are traveling collinear. There are different stages during the impact, and keep this in mind. Impact happens in a very short period of time, most often like a split second or even less. Here we are examining it in a super duper slow-mo motion mode to understand the physics behind it. So we have stage 1. This is the instant just before the impact. This is when M1, M2, the 2 tennis balls, still have their separate velocity, v1 and v2. They are not in contact yet. Stage 2 is at the maximum deformation during the impact. At this time, M1, M2 are stick together, they contacted in full, and they are moving together. And we'll use v0 to represent the velocity of this special moment. We'll use that later. And then we have stage 3. This is just after the impact. The 2 balls just got separated, and there's no more deformation of each ball, and they both have restored to its original shape. At this stage, M1, M2 have a new velocity, and we'll name it as v1 prime and v2 prime. And you'll notice here I use the length of the arrow to represent. In this specific example, v1 start with greater than v2, and after the impact, v1 prime is smaller than v2 prime. This is where we can imply the conservation of system linear momentum. If you recall section 3.9, if we look at these 2 balls as a single whole system, we can take the assumption that forces except for the impact force are small enough that can be ignored, such as friction, air drag. Therefore, G before impact equals to G after impact. This gives us the stage 1 linear momentum equals to stage 3 linear momentum. And we can replace G with proper variables using the linear momentum equation. We have M1 V1 plus M2 V2, stage 1, equals to M1 V1 prime plus M2 V2 prime, stage 3. Looking at this equation here, we only have 2 unknowns, V1 prime and V2 prime. The 2 unknowns and 1 equation. There is something missing here because we cannot solve it yet. And we came up with this equation by just looked at stage 1 and stage 3. What about stage 2? Has to do something here. Why? Otherwise, I'm putting it here. Stage 2 is when the max deformation of both objects happened. And let's zoom in again to find 2 more substages just before and just after stage 2. We'll call this stage 1.9. This is when they just touched each other and the deformation is just about to start, and we can say their original velocity, v1, v2, is still there. Okay, they just got touched. And then we have stage 2.1. This is just before they're going to separate. They have completed the impact, they're going to separate. But just before they separate, they are still in touch. At this stage, both of them have almost restored its original shape, let's say like 99.999% restored. At this time, their speed is going to be infinitely close to their final speed, v1 prime and v2 prime. So why do we need stage 1.9 and stage 2.1? Because we can add the force component here. At stage 1.9, they are starting to deform. So there is a deformation force. We can call it FD, deformation. This happens from time 0 to time t0. And note that t0 is a time at stage 2 when the max deformation happens. And then at stage 2.1, they have restored most part of themselves, but they're going to separate. They have not separated yet. There is a restoration force still exists, and we can call this FR, the restoration force. This restoration force acts on these two objects from T0, stage 2, to T, representing stage 2.1. Okay? And we're almost ready here. Just to recap quickly, before the max deformation, there is a deformation force, and after the max deformation, there is before separation, there is a restoration force. I want to introduce a ratio E here. Ratio E can be used to measure the magnitude of restoration impulse to the magnitude of deformation impulse. And we know how to calculate impulse, right? So this ratio E has a special name called coefficient of restitution. For M1, we can calculate E. After some arrangement, it's V0, the maximum deformation moment velocity minus V1 prime over V1 minus V0. For M2, we can also calculate E, and we get V2 prime minus V0 over V0 minus V2. And this ratio is the same for the same object or same impact. Therefore, either from M1's perspective or M2's perspective, they are the same. So that's why we all call them E. It's no E1 or E2. They're all E because they're impacting each other. This moment, this impact has the same E. Given that, we can equate these two equations given by M1 and M2. We'll now eliminate V0, the velocity at the maximum deformation, and end up with a ratio E is given by V2 prime minus V1 prime over V1 minus V2. In word, this is relative velocity of separation over relative velocity of approach. Remember, we had one equation with two unknowns at the beginning. Now we have another equation with two unknowns. In total, now we have two unknowns, and there are two equations. They are absolutely solvable. One is coming from conservation of linear momentum, another one comes from coefficient of restitution. The coefficient of restitution can be used to measure the type of impact. As I said, for the same type of impact, the coefficient E will remain the same. Whether it's the perfect elastic impact, E equals to 1, with totally no energy loss, or it is a perfect inelastic or say plastic impact, then E equals to 0. This means the energy is entirely lost. So E, the ratio E, can be any value from 0 to 1. So far, we only talked about direct central impact. Are we going to spend the same amount of time to derive equation for oblique central impact when two objects are not moving in collinear? Well, not necessarily. What we know about direct central impact can be used here with some modification and change of mindset. If two objects are not collinear, we can set up an NT coordinate at the point of contact or point of impact, and N direction is called the line of impact, and T direction is called the line of contact surface. Then, for each object, we'll break their velocity into N and T directions. For the line of impact N direction, we will treat it as a direct central impact motion, as we did for the entire video. Apply the conservation of moment of system and use the coefficient of restitution. And in the T direction, the line of contact surface, if there's no friction and any other major forces are involved, velocity of each particle at the T direction is the same before and after the impact. And you can see M1 V1T equals to M1 V1T prime. So v1t equals to v1t prime, v2t equals to v2t prime. So we don't need to derive the equation for oblique central impact over again. We'll just break the motion into nt, and n direction will treat it as the direct central impact, and the t direction will have no velocity change. This concludes our discussion about impact. Please review these recommended readings. Thanks for watching. I'll see you next time.